Okay. Hello. What are you doing here? Right. Thanks for coming. So, I think we are in a good situation in the sense that, well, first of all, we are in a terrible situation since you are here on Friday evening. But I think we are in a good situation in the sense that we will be able to cover what was planned, okay? Which is good news. Well, depending on what you mean by the plan to cover. So in this sense, by construction, we are in a good situation. Good. So before we start, any questions about either logistics, plan, or anything? Okay, all good. So I think we were discussing last time the differential transition amplitude or transition probabilities, right? And we talked about the decay rate, and we talked about scattering amplitude or scattering cross section. So let's just briefly write it down. So differential, now we know probability. Transition probability. So differential transition probability per unit time. We found out that there is this factor that goes to the initial state. So this equation is valid, as we talked about, when either initial state consists of one or two particles. So there's that. Then there's a invariant Feynman amplitude. And then there was this relativistic density of state. So explicitly, this had a total momentum conserving delta function. And then for each final state, we had a summation over all momentum configuration weighted by this line. Okay? So that was the case. And as a first discussion, we talked about differential decay rate. So in this case, we had a single decaying particle, so 1 over 2e. And then whatever amplitude that 1 goes to n number of a final state. And then we had this differential, relativistic density of state. And then we talked about the fact that everything else here is Lorentz invariant. So we spend some time thinking about, therefore, Lorentz transformation property of the gamma is completely locked in this vector. So, therefore, we found out that the decay rate in the frame where initial particle has an energy E versus decay rate, the particle is in the at rest, so the total energy is just a mass. Therefore, is given by this factor, right? So that gave us, so for instance, if I call inverse of that to be time scale with in principle energy versus this, and then just by the fact that this goes like a gamma times m, we see that which way I should go? Gamma up, gamma down, gamma up, gamma down. So they give us now precise definition that this actually equals the lifetime. Right? So how long it takes. So that was the first discussion. And then we also talked about that differential cross-section. This is when two particles goes into n number of particles. The same, so nothing different. So now in this case, I have a two initial particle. So I have this as a factor, and then 2 to nf square, and then that's it. Again, this is a relativistically invariant, and then we spend time thinking, oh, again, I'm making the same mistake, right? So cross-section, I define the differential probability per, so let me actually write. Differential transition probability per time and flux. So meaning given collision, the probability. So that introduces this flux factor, as we talked about. And again, continuing our discussion about the Lorentz transformation property, it captures that, and then basically this vector, using the fact that velocity can be written relativistically as a p over e, allow us to write down, for instance, if I consider the situation where a particle moves along the x direction, and then do the collision and something. So this can be written as epsilon 2, 3 mu nu, and the first particle mu, second particle mu. Therefore, confirming the fact that this object, cross-section, is not Lorentz invariant. However, it is invariant under 0, 1 sort of rotation, which means that it is invariant in the boost along the collision direction. So that's what we talk about. Okay, so then today I will finish up this part of this discussion by actually, considering this for the 2-to-2 scattering and actually looking at computing this density of safety factor explicitly. Therefore, we get a closed form of the formula, and then discuss a few features about that before we move on to Green's function discussion. Okay, that's the goal. So let's consider 2-to-2 scattering. So the goal is to compute this, first of all. Okay, so let's just do the computation. So let's see. So this one has, so probably, okay, I don't mean exactly that. Oh, there's the eraser here. Oh. Okay. So other than this vector, everything is a kinematic vector. So basically, we want to be able to compute this as a cross-section, if you like, for 2-to-2 scattering. Takes the structure that it has a this. So what is that? It is D3, P1, or P1 is bad. Is P1 bad? I mean, other than this, is P1 bad? Not necessarily. P3, P2. So this is the first final particle, okay? This is the second final particle momentum, okay? So I'm writing down this Pn. Okay, so and then I have a 4, E1, E2, and then what do you have? And then, well, sorry, okay. Let me factor this out. This is not, so anyway, now you understand that this is the first final particle, this is the second final particle, but then I just want to, that really clashes. This is the problem of my lecture. Ta-da! Guess what it is? 3 and 4. That solves every problem. 3, 4, okay? And then we still have that factor. So let me clean up. Ooh, really wish I had that function. Do you have a clever suggestion? So I screwed up a little bit, but I'm gonna do it. E1, E2, V2 minus V1. So that's that. Okay, so far so good. If you like, you can put it out of integral. Now, so and then we have a momentum conserving delta function. And we write P3, P4 minus P total. Okay, and then we have this. Okay. So what I'm gonna do is that, I'm not gonna worry about these factors. So let me define. Basically, I want to evaluate this integral as much as I can. So I just want to put this as a start. Okay? So, okay, I'm not worrying about that for now. So let's just focus on these kinematic variables. So what do you do? So first, this is equal to delta 3 of momentum, 3 momentum minus total momentum, and then delta of energy, total energy. Okay, obviously. I can therefore perform the P4 integral just eating up this vector, right? So that will give me, what did I get? So I'm eating up the 2 pi to the cube, and then I have 2 pi to the cube downstairs, so I still have that. So what I will have is a d3p3 over 2 pi squared times 4 times d3, d4. And that integral is gone, so I have only energy delta function left out. But obviously, now everything, whenever you see E4 and E4 here, you understand that now. And then I'm in the center of momentum frame, so I'm gonna set this to be 0, okay? So I am in the center of momentum frame, so I'm in there. Remember, I can boost along the collision directions, I can do it. So you understand that therefore, after I've done this delta function integral, there's this relation. So whenever you see E4, momentum appearing in this expression is same as the square of the P3. Okay? Am I mixing so far something? I think I have everything, and then I have a sum. Yes? Are you with me? Yes? Okay. Good. So now you just need to do this integral. Okay? So how would you do that? Well, let's hopefully standard technique to do. So delta function. So if you have a delta function of a function, then what does it do? What would you do? You take the derivative of this with respect to the argument, the value added at x0, where x0 is the 0 of the function, and then delta x minus x0. Well, if you have more than 1 at a 0, obviously you have to sum over that factor, but for now, it's sufficient to consider this case. So that delta for ET, again, understanding that P3 momentum appearing here, sorry, P4 momentum appearing here is basically the same as P3, the magnitude is the same. So what we have to do is that we need to do 4 with respect to, I want to do P3 momentum. So because I'm going to write here P3P as dP3, P3 squared, and then solid angle. So basically, I'm interested in integration over P3, the magnitude of P3. So I want to do this. And obviously, I don't have to worry about it because this is the fixed energy once I know which process I'm talking about. So this is basically the numerical number. Okay? Okay, so this is what we need to do. Inverse, if you were panicked. And then 0. You know what I mean by 0. Okay? So the 0 from this function. So let's just evaluate that. So what is it? E squared is m squared plus P3 squared. And then what is this? Which is m squared plus P4 squared. Once again, because of the previous delta function calculation, it is equal to that. So let's take a derivative. So I have a 2 E3 this, which is equal to 2 P3 dP3. And so I get dE3 over dP3 is equal to reciprocal of that. Right? P3 over P3. Good? So here too. So if you do the same thing, dE4 over dP3 should be reciprocal of that. Done. Okay? Right? Good? All right. So, let's keep this formula. Maybe it becomes useful at some point. I'm looking ahead. Eventually, I want to be able to write a complete answer here. So, therefore, this delta function, continue. What is it? So that is this plus that to the overall inverse, right? That plus that to the overall inverse. So what is that? That is basically E3, E4, E3, ET. So that's the sum of the two. Do you agree? So first I'm just doing this thing. So I added up that top and then combine. That's that to the inverse delta E3 minus E3 and 0 for the whatever that is. Okay. So let's see. So then sigma. So I was doing this calculation. Let's clean up. So let's clean up a little bit. So I need to do B3, or not BP3. Okay. So these two factors cancels out these two factors nicely. And then in the new denominator, so that gives you 16 pi squared. Again, I'm doing this. So I have ET P3, but from now on, let me just call P3 to be the magnitude of a final momentum, because I'm in the center of momentum frame. That's my PF momentum, so that. Oh, what am I doing here? So I already did, so I have a denominator, this guy, ET times PF, but I had a PF squared, so I'm canceling the factor. And then d omega times the rest. Good. Almost done. Well, it's quite doable. So let's now just to take care of this. This I cannot do in general because this is all the dynamic information, right? So this is theory dependent, but I should be able to take care of that. So what is that? Which I already did it. So this is 4 times, remember? Let me just rewrite. So remember V, in order to clean that up, remember V is a P over E. So that is given by P, so let me just write, just do it 2 steps. E1, E2, so V2 is what? P2 over E2, and then this is P1 over E1. Okay, so that's what we are doing. So that we can combine it together. So that gives me 4 times P2 E1 minus E1 E2. Again, if we are in the center of momentum frame, the size of these two is the same but opposite, right? So you can pull it out. So that gives me initial momentum size. And then you get E1 plus E2, which is nothing but total energy. Okay? Right? P2 is minus P1. So actually you sum up. That's the magnitude of initial momentum. And then you has E1 plus E2, which is total energy. So now, if you combine everything, what do you get? So I should do it. I was anticipating. Boom. Is equal to. Okay? I just have in the denominator that factor. So I have a 64 pi squared. Okay? I have ET squared. And then I have PF over PI. And then entire dynamic information. And finally, this is differential cross-section. Differential with respect to the scattering angle. Okay, this is the solid angle. Which direction these two particles goes in. So this is nice. This is very close to form formula. And for any two-to scattering, so this is true when this is true. Okay? So for any two-to scattering, this is the general formula. Okay? And then you can go one more step. So now, if we consider elastic scattering. So what is elastic scattering? Elastic scattering is, you just collide it together and then the same two state comes out after that, but only with some momentum transfer. Okay? It's not like you shoot into electron positron, all of a sudden produces a Z boson split into Higgs plus or something else. Okay? This is inelastic because you sort of merge into something and complete it, creating very different state. But this is elastic in a sense that the same initial state survive in the final state, but only with a different kinematics. Okay? That's elastic scattering. So for elastic scattering, since by construction I have the same particle in and out, which means they have the same invariant mass, which means the same size of the initial momenta and the final momentum. You understand? By energy momentum conservation. Right? Energy is the same, but energy is the basic square root of m squared plus p squared. But m is the same, so p squared should be the same. Which means that for elastic scattering, what do you get? Basically, the size of initial momentum, free momentum, final momentum is the same. So you get this nice formula, this 2 to 2 elastic is equal to 64 pi square et square in case you remember, what was the dimension of amplitude for 2 to n? It was 2 minus nf or nf minus 2. Who remembers that? Huh? 2 minus f? Good. So for 2 to the scattering, this becomes 0. So this is dimensionless quantity. And so entire dimension minus 2, area, cross-sectional area, is already captured by order of et squared. So this just, provided some dimension is strength of the process. It also controls the kinematics. I said that it also controls the kinematics because this is a function of, in principle, theta, and then p, right? So it will provide a different way depending on which, scattering angle it happens. Good. So that's a nice closed form formula for cross section. So hopefully now if you're given some simple theory, right, then you should be able to do principle complete through the scattering formula, differential cross section. And this is one of the key objects obviously measured in LTC, and you see these distributions. Okay? Good. Let me just make one small comment about this. So that is this. So note. Oh, by the way, if you care about that, so you may have seen cross-section in the context of non-relativistic quantum mechanics, right? So if you have taken quantum mechanics class, say in a grade school, Sakurai, or whatever, you might have seen the formula that cross-section is equal to, so this is quantum mechanics formula, like strength of some f function, theta equal to d squared. Okay? So this basically a derivation of a full non-relativistic quantum field theory of that formula is seen, and you can see the matching of this Lippmann-Swinger equation, and you derive this thing, and then this is exactly that, and in this case, even single out, which is a kinematic factor, which is dynamic of energy. Again, another last small comment I want to make is the following. So consider in a theory, QFT, with, say, time reversal symmetry. Okay, so suppose you have some hypothetical theory where that QFT preserves time reversal. Another way of saying it is that it preserves the combination of CP, okay? Because I discussed to you, even though I did not derive, but I talked about the fact that it is believed that any QFT, which is a Lorentz invariant, and respect to spin statistics, then it preserves the CPT as a combination. So since it preserves the CPT, if you break one, that means it breaks the other two. Okay, so that's equivalent. In fact, the standard model does not respect the CP. But suppose you have a QFT that preserves the time reversal. So then easiest way in this context to phrase is that if you had a process where this thing goes to I to F, okay, some initial state to final state. Okay, I don't even have to specify specifically what kind of initial final state I'm talking about, but I don't know if you like. Whatever you can. This is probably too simple. Let's talk about like that process, for instance. 2 pi goes to n or n bar, if you like. Okay, but now time reversal says that this should be equal to this process. Okay, this is where all the dynamics is equal. But then you can ask, does that mean that you should expect at the level of a cross-section, you should get the same cross-section? So then, does that mean that cross-section, or even differential cross-section, if you like, okay, for initial to the final, had to be the same as differential cross-section of F to I, right? And note that this differential rate is a product of a dynamical factor and a kinematic factor, right? I stressed it out. So here, dynamical factor and then kinematic factors. And in this example, let's just consider elastic scattering. Well, that's not elastic scattering, but let's consider the case of elastic scattering. Okay, sorry, actually, let's go back here because elastic scattering is too sort of constrained. Let's go back here. Remember, this is general. Any two-loop scattering satisfies this. And then, there's a dynamical factor and the rest kinematic factor. So in general, this is not true. Even in the theory that has a time reversal. So the dynamical factor has to match by demand because it is demanded by the symmetry. But for instance, you can easily see that, here, one of the kinematic factors you see, this is proportional to this, but on this side, it will be proportional to that. Okay? So there's no reason that this is equal in general. Suppose you had a light particle pi turning into heavy particle n bar. Right? Energy is preserved, so for the same energy, they can carry larger momentum than this. Right? So therefore, in this particular process, this is smaller than that, which means obviously this is bigger than this. This ratio is bigger than that. So by kinematic factor, even if in the theory with the time reversal, cross-section can be different, which is in this case because of kinematic structure. Okay? All right, so that concludes this part of the discussion. Any question before I move on to somewhat more now? Slightly more abstract, but hopefully it's slightly more, not slightly, but another interesting to think about. Yes?
I think I missed the last part. So it has to be, it should be, so there is a conclusion that the cross-section does not preserve the time reversal symmetry while the amplitude does.
Probably precise, more correct way of saying it is that even if you have an exact time reversal, even though because of time reversal symmetry, amplitude has to respect that, but even if everything is completely time reversal invariant, cross-section need not be the same as an observable quantity. So as a physicist, you should not be like panicked. Oh, cross-section is different. Oh my God, this theory is not time reversal invariant. No, you have to divide. You have to separate carefully. What encodes the symmetry? What encodes the kinematic? That was the point.
그럼 토탈 크로스-섹션은 시메트리에 하게 나오는 건가요?
So if you actually integrate,
Yes.
Total cross-section. So let's see. So whether these two guys meet each other versus whether them got each other. I mean, we will know if we actually do this integral. This integral can be done. Right? This is a solid angle. Basically, this captures a single this cross-section angle, and you can do that now. I'm not sure if we can make a general statement, because depending on the speed of the particle versus scalar particle, there's different angular dependence, and this integration can be different. So in other words, whether initial particle is all a scalar versus the final particle include a spin particle for a muon and boson versus not. In principle, this can have a different dependence on that. But regardless, I'm not sure this intrinsic difficulty can be overcome somehow magically. So I would expect that even total cross-section may not be equal, in the sense that why would we expect like pi Pascal in total cross-section will necessarily be equal to n cross-section? But that's a good question. Maybe you can at least do the one computation for this very simple type, a simple model, actually see whether that they actually numerically the same or not. Let me know. Okay, any other questions? Okay, so now let's move on to a different topic. And this will be like last sort of topic we discussed this semester. So that last topic that we want to talk about is so the motivation is this. So what is that, and why we need to even think about that? Motivation is so far, okay, we consider the diagram. So we have seen this type of block, whatever. Okay, in general, there's this block we talked about, and we can take again the same convention as that. Momentum goes in like this. K1, K2, K3, Kn. So far, we only considered diagrams with external lines on shell. Okay, by which I mean all the momenta satisfy on shell condition. Okay? Okay, so you might say obviously, because we wanted to think about scattering processes. So we know that we prepare actual particle as an external particle, smash them together, see what actual propagating particle comes out. So it was a correct question to ask, and then look at therefore diagrams. In particular, since this diagram lives in the momentum space, not just any diagrams, in this case actually Feynman diagrams, okay, with external legs on shell. Okay? Now, it is actually useful, turns out to be useful to consider diagrams with external lines actually off shell. Okay, so in this part of the lectures, in this part of the discussion, we will study the diagrams with external lines on shell. Okay? So let's see why it can be useful, and then we will sort of develop a formal structure, formal machinery that can sort of handle those objects in a single package nice way. Okay? So why they can be useful? So let's consider the example. Let's just go with the concrete examples. So for instance, we consider diagram of this kind. This, for instance. Or you could have considered this type of diagram, which is a well-known diagram, but anyway, diagram. Now, we're again going to assign the momentum that everybody goes in towards the block. In this case, the block is this. This is the block with the one-loop structure. And we are going to allow that Ki square is not necessarily equal to its mass square. So we actually consider off-shell diagrams. So first of all, if we want to get these Feynman diagrams, for S matrix, simple. Just to take everybody satisfying on-shell condition, and obviously that diagram can be used already for scattering amplitude, so no problem. On the other hand, keeping off-shell is useful. So for instance, these diagrams can appear as sub-diagrams of bigger diagram, for instance. Again, let's just take the example. So let's see, I should be creative. How much I can be creative? Or and so here, boom. This. Okay, so the point is simple, as you see. In this part, the diagram that I draw possibly can, with the off-shell momenta, can be identified as this, and then this in this diagram. This was the diagram. But if I sort of know how to handle diagram or object with external momenta off-shell, then if I know how to compute that and how to organize that, I can put into the bigger diagram, right, as a module, and it still works. Because in general, if this diagram appeared here, even if you impose a momentum conservation at every vertices here, you can show that, and you will see that these momenta are not necessarily on-shell momenta. Okay, so you will spend much more time thinking about loop diagrams and why these, for instance, legs appearing in the loop may not be a non-shell. So that's the question, and then a task of renormalization and so on and so forth. So those guys, even if every point satisfies energy momentum conservation, but in general, these lines do not respect on-shellless. Okay, hence it is interesting and useful to develop a machinery that allows to deal with this object. Okay, so that's just a quick motivation. Now let's just jump in and think about how to deal with that. Okay, is that clear? What we are going to at least deal with and why we are going to deal with that? Okay, so let's just then go on. So here I want to define, therefore, because I know what kind of object I want to talk about, let me define a G tilde of n, which is a function of, say, k momentum. So diagrammatically, I will represent this as a block with n external legs. Therefore, I will have a n momentum, but I will use the convention again, all the momentum goes towards the block. So this definition of that function, which is diagrammatically represented as that, is the sum over all diagrams, meaning this is in all orders in perturbation theory, meaning now this block can include not just this, but it can include higher order and higher loop diagrams, everything, okay? With and obviously external legs such that all Ki go to the block, so it goes inward, convention, this is convention, okay? And all for momentum conserving delta function included. And then I want to, this third condition is important. It also includes propagators for external lines. So for instance, if we talk about the scalar particle, okay, which we've been only considering so far, so that means that I will include for each external x, Ki squared minus mi squared plus h. Okay, so this one is different from the Feynman amplitude. In Feynman amplitude, it did not include external lines. Instead, for external lines, we just attach to 1. If you remember Feynman rules, so they will compute it. Here, we're going to include all the propagators. And that makes sense if you think about this diagram. So if you want to have a module that you can just attach to a bigger diagram, obviously in this thing, this appears as an internal line. And this internal line must have the associated propagators. Right? So then, therefore, if you just construct this entire one, starting from this bigger one, and then just put it into the smaller one, and that smaller one, you can take a convention. If you already included the propagator, you know, just attachment. And finally, I will define this object as including both connected as well as disconnected diagrams. So it includes everything. So far just the definition. Okay? So I just defined an object. Now we are about to start using it, understand the properties, and so on and so forth. Right? So now I defined it. Okay. Any questions so far? So now we're gonna build up machinery all the way up, and eventually you will see pretty beautiful formula. But before we jump in, let's take the example. Okay. Again, let's take the example where we like. So, for instance. Let's consider in this theory, suppose I want to look at this block. Okay? So I have a K1, K2, K3, K4. So this will be G tilde of 4 with 4 momentum. So let me just use a simple notation to denote that. So let's ask, what are the diagrams we're talking about? So we're talking about the following diagram. The Feynman rules for this thing is K. So this is dashed line. So one case can be K1 is connected to K3, and K2 is connected to K4. So there's a momentum flow. What else? It can include K1 connected to K4, K2 connected to K3. What else? K1 connected to K2, K3 connected to K4. So these diagrams, so the first layer, so these are order G to the 0 diagrams. So no vertices are appearing here, right? And you can check yourself, and there's no any diagram appearing in G to the 1, G to the 2, G to the 3. Next order you will appear is something that we already have seen. So there's this diagram appearing. Okay, so this is order G to the 4th. And then you can keep include. So this single function, or single diagram representation, include all orders in perturbation theory diagrams with the specified external links. Okay, so hopefully you have a sense. So this thing includes everything. So what types of function are we talking about here then? So for instance, that function will be as an explicit function. So let's first talk about the first thing. Like I said, we have to include the propagators for the external legs. We have to impose a momentum conserving delta function. So for instance, for this first diagram, I know that the momentum k1 plus k3 should be conserved because the convention is that momentum comes in like so. Right? So that means that we will have 2 pi to the 4th k1 plus k3, and then propagator, so k1 squared minus m squared, pi, if you like, after we can write epsilon. I'm not done yet, because the lower part, 2 pi to the 4th, k2 plus k4, k squared minus m squared. Okay, so that's the amplitude for the first diagram. And then you will have all other terms. So let me just say blah, 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 blah. Okay? Now let's ask the first physics question. So suppose we have that object. We can ask, how do we extract S metrics out of it? Because as big class of observable that we are interested in is S matrices, transition amplitude. So you can ask, important question is, given these types of object, Ki, okay? So you might say, yeah, sure, you define whatever you like, but is it ever useful, right? So once we have this, how to extract S matrix. So for instance, in this particular example, is it possible to extract this from K2 to the 4th? Or in general, if you are given this plot, how would you extract? Well, probably you already have intuition. What did you do? Well, in order to do the Feynman diagram computation for the amplitude and therefore compute the eventual S matrix and then differential rate, you computed it without the external leg propagators, right? That's what you did. Otherwise, this is basically the same set of diagrams. Other than the fact that this is a fancy object, which can include in principle in any diagram and any order in the G expansion. So therefore, you need to do two things. First, get rid of propagators that this definition of this G tilde function included it, so you can get rid of it. And then you have to impose on-shell list of all these external legs, right? Because this is defined, in general, external legs are on off-shell. So therefore, in order to extract the S matrix, let's starting from
손이 하나 떨어졌네. 손이 하나.
this is Mike. Oh, yeah. Thanks. Like this. Work? Yes? No? It doesn't? How about that? Oh wait, no, it's not. Battery's out. Battery's out. Emergency. Emergency. But not for me. Not for you either. Whoever is not here. Emergency. Good luck. So if you are given this, the question is how to extract this, right? So it is well defined because what did I say? Two things. Get rid of external propagators. It's called amputation. I mean, it's a horrible word. Amputation is cutting your legs and arms. I mean, it is one use to do. There's a value, right? The external legs. Sometimes you call that way. So we amputate and then put on shell. So formally, how would you write? So suppose I label the external legs as a 1 to 4 in this case, but you can just write it as 1 to n, and then you impose on shellness, but after amputating it. So how do you do that? KR square n1 squared plus I is 1 to the I. That was a propagator, but I get rid of it, right? Inverse. Then g to the 4. Okay. Is that clear? Yeah? Amputate, impose on shot. That's what I did. Okay? Now, let's keep playing with this. What is the really physical meaning of this, other than the fact that it's useful object to define, and we know how to describe the S matrix? Is there alternative or independent physics meaning of that object? You can ask that question. Okay? So to do this, to answer that, so that will be partial answer. By the way, let me say the following thing. As you see here, I take the mode of building things up from our exercise or intuition from the tree-level physics, right? Meaning tree-level physics, I mean, like, we never learn how to deal with loop diagrams and so on. So here, what we are doing is that based on the exercise and learning we have done in QFT, mostly at the tree level, and then simple calculations. Here, I'm sort of motivating the object based on that. And I'm saying this because eventually I will define some object which is valid in all orders in perturbation theory in general. But here I'm just playing with it at tree level, and then we will learn some good aspect about it. And then eventually I will ask, can we promote this thing to that works at all orders in perturbation theory eventually? So we want to have this glorified object which is working at any order. Okay? So now I'm just playing with the tree level game. Good. And eventually you will see that there's some other modification factor should appear here, therefore, if you go to the higher loop orders. Okay, now, so in order to understand whether there's any other alternative physics meaning to this object, let's actually do the Fourier transform, which you learned how to do it. Did you? So let's do Fourier transform. So then you can, now without a tilde, so x1, 2, first of all, this can be defined as, oh, yes, 4kn, and then e to the, who remembers the convention, k1 dot x1, kn dot xn, g to the n. Okay, I have to split it. Kn. Okay, so far I haven't done anything. So to really understand the physics meaning of this, now I want to play a somewhat different game that you have done. You have seen it before. Let me prepare space. So in order to understand the physics meaning of that, I want to do the following thing. So now consider doing the following. So you had a theory based on Hamiltonian density. That Hamiltonian density has a, say, free part, and then it had some small interaction part, right? So for instance, we consider the equivalent equation. Now, I want to add so take this, and then I want to add one extra term. So rho x, phi x, for instance. Okay? So this phi already appeared here. For instance, this had a phi, psi bar psi. For instance, this was still one of the field appearing in the original theory. Here I just introduced new object. And that object, rho, is ever named. So first of all, this is a classical configuration. Such that, let me write the name, let me write the expression, but this property. So what does that basically mean? This is a configuration, random configuration, not turned on by any quantum sort of a source, but it is a space-like in the space and time sense. It is only a localized support. That's what this expression roughly means. So if you don't like this expression, that's okay. I just mean that there's some function of a space and time, and then it's just activated only in the localized manner somewhere. Okay? And this type of machinery or object that we use in quantum field theory is called the source. Or sometimes it also plays the role of detector. So we are about to play with the source, and then this will turn out to be extremely powerful and useful concept. So now, with the introduction of this source, all of a sudden you get extra diagram, an extra picture that you can talk about. So there's an additional diagrams. Wait, so suppose, I used the data. So this is again rho. Then this linear interaction, this linear term, right? This is not quite again quantum fluctuation. This is a classical source. And then somehow it can turn it into whatever excitation controlled by quantum field phi. So you get this picture, therefore, given this, either you can imagine having a process where particle associated with phi gets created, hence source. So you have a, let's say, laser beam source. It creates the photons. And there's some classical stuff, meaning there's this device you can click it. Right? There's a classical configuration, localized in space and time, can shoot the laser beam. It's a source. Or you can have a picture like this. So you have something, and then you can detect, I saw a photon. So for instance, a collider, right? If you look at the picture in the LHC, there's a CMS Atlas 2 gigantic detector. Then some physical process happens in shooting out the particles, and then they have a ton of detectors. And then as some particle passes through, you can tell, there was electromagnetically charged particle, something. So the detector is organic classical configuration, right? So macroscopic size. So in this case, this plays the role of a source. This thing plays the role of a detector. It detected. Now, but let's ask the same types of question we were asking. So given this new interaction, okay, I put interaction because this does not describe interaction among in actual quantum excitations, right? This is an interface between classical and quantum. But we can ask, what is the final rule? What is the final rule for this? What is the final rule for that? We can ask the question. So let's just work out this example, and then you will see quickly what this needs to be. So hopefully you understand how you need to translate this question. Okay? So that's what eventually you want to know. Given this diagram, what is the correct formula you want to write it down to answer the question? What is this? So you started out with something that didn't have any particle. And then somehow there's interaction Hamiltonian gets injected in, and it ended up creating this particle with momentum T. Okay, in this case. So what you want to ask is, starting from the vacuum, according to the Dyson's formula, something converting into a particle with momentum K. That's what you're asking. And then Dyson's formula, you inject Ui, minus infinity, plus infinity, that type of object. But here we can ask the question: what's the first order in this expansion, treating that additional vertex as a new sort of interaction. So therefore, here you're going to have minus I integral. So this is not a linear order. Let me actually write here. So this thing will be time order e to the minus e for x interacting Hamiltonian in the interaction picture. So that included that new vertex. That new interaction. So in linear order, you're going to have, I need more space. Rho of x, pi of x, vacuum. That's what you're asking, yes? So nothing injected particle out. That's the picture. So this thing had two terms. One is alpha p e to the minus ip by x. And then let's just consider a real scalar e to the plus ip by x. So vacuum, and this thing is what? This thing is alpha dagger acting on the vacuum to the dagger, right? So that means that this is the vacuum alpha with k. Yes? That's how we define the one particle state. So therefore here you see that what you have to use is this creation part. There's alpha dagger that can give you non-trivial commutator, non-zero answer. Yes? So therefore you see that if you just work it out, alpha k, alpha dagger t, there's a commutator you can commute. That give you 2 pi whatever e to e something. You cancel out all the factors appearing in the momentum integral of this thing. So you should therefore get eventually, you pick out the plus one, but there was a minus I here, so minus I, and then if you do the momentum integral, you get this basically. Do you want me to work it out? I feel like I'm probably rushing too much. Are you ready? Okay. So, vacuum alpha k. Good? Minus I p for x, rho of x, p, e, p. At least we know what to use. P e to the plus ip dot x, vacuum. Oh no, I forgot one factor. Not because I was rushed. Alpha. No, alright. No, right, good. Right? Yes? Good. Now, that gives me, if you add and subtract, k, p is 2 pi q delta 2pp. Remember that? So that gets rid of this, and then 2 pi to the cube from that, and then delta function, you can perform this integral. Yes? So then you will get vacuum minus I p for x. But remember, this is same as imposing on-shell condition. Also remember, this also requires an on-shell condition. So eventually it will be d I p rho of vacuum. Are you with me? Hence, what is it? This is known as a Fourier transform, right? This should have been k, right? Because the delta function imposes p to be equal to the k. Yeah. So k. Yes. Was that better? Okay, so therefore we learned that this diagram, the Feynman rule, let me write in red. So this thing, creation part is minus I because of 4s is minus I, rho k. What about this? Well, this is literally the same, but reversed to the k to minus k. Remember? So that is still the same. Minus k. Right? In, out, k to minus k. Okay. Good. So now let's play. We just introduced this source term or detector. And then remember, we were still playing with the Gn function, right? Which we defined as a collection of all diagrams. Now, this is now becoming useful in the following sense. So with now this new vertex, rho of x, phi of x, there are additional diagrams. Well, that's what I said. There are additional diagrams, but not only that, now we can think about the following diagrams. So for instance, I have a block. But previously, this was just literally propagating line, right? Although it was off shell. So now I can attach to this. I can look at the diagram where ending point is all these source terms. So everything inside is G tilde N of Ki, and then I have these source terms attached. Okay? Now, formally, in this modified theory, where on top of this I have this phi of x, and suppose let me just call this prime G of something, some operator. Something. Just be concrete, let me actually write down. So this theory has two expansions. One in powers of G, another powers of rho. Remember, rho is a classical configuration. It is not a quantum operator. Okay? And in fact, final rho is weighted by the rho tilde in momentum space. And for a reason that will become important later, let me mention now, and probably you want to remember, although I will mention again, final rule in this example is a momentum dependent. I said that, okay? It will come back soon. But final rule for this thing obviously was not momentum dependent, it was minus I times G, all, right? That's momentum dependent, which will come back again. So now, looking at this, again, this thing has both, this theory has one G expansion, that was original expansion we had anyway, and then now this thing has a rho expansion. For now, I'm going to focus on only rho expansion. Okay? So let me define the following object. So I will call Z of rho, which is an object which only captures the expansion in the rho. Okay? So let me write explicitly. The sum over all powers. And then I'm going to expand in, and then I have a momentum integral. So D4 K1, D4 Kn. And then I will have a Gn Ki. So I'm just writing simply just Ki, and I made K1 to Kn. And then I have this here. So let me explain why this is I consider that. Number one, you can just view it as I want to have some formal machinery which gives me a expansion in powers of rho only. So for all powers of rho, okay, and then I just define a coefficient with the proper combinatory factors. Remember, final rule was minus I rho tilde. So minus I to the n, and then nth power of rho tilde is literally this final rule. If I look at the nth power in the row. And then the coefficient is this object. But I define this object precisely as a G tilde to the m. Okay? So that's that. These were swapped over, so I'm just doing the momentum integral over that thing. Okay? And so everything is good, and then I'm doing the expansion in the rho, powers in the rho, so I'm actually doing this perturbation theory if you like. And G expansion perturbation theory is all encoded inside of the G tilde object. In fact, I define the G tilde as sum of entire diagrams in any order in the G expansion. Okay? So this is a non-perturbative in G expansion, but explicitly expansion in G rho power. Is that clear? Now, what about this 1 over n factorial? What about it? It's cool to have that. But you may recall, if you ever remember, that when we go from the Wick diagram to Feynman diagram, was, oh God, I would never want to talk about that ever again. So when we go from the Wick diagram to Feynman diagram, which was a diagrammatic expression for the operators living in the position space, to diagrammatic representation of the diagrams in momentum space, which is useful for the scattering amplitude. we talked about the fact that given a one Feynman diagram with n vertices, if you do the arbitrary permutation of those n vertices, you get the same amplitude. Okay? So Feynman diagram is a function of only momenta. And so if you permute the vertices, which is the Poisson space data, you should get the same function of momentum. Hence, we said that in the Dyson series, you get 1 over n factorial because you expand the exponential. But for any given diagram, you have your n factorial permutation of the vertices. So basically, it cancels out that. So let's not worry about that permutation. So we say, okay, we're just going to represent the Feynman diagram without labeling the location of the vertices. Because we are going to anyway add up to all those n permutation of diagrams, and then we're not going to worry about the sort of n factorial. That's what we said. Now you might say, what about it now? So this is a Feynman diagram still, but off-shell external momenta. Why I'm putting this 1 over n factorial? Did I lie? So that's where this factor kicks in. Here, Feynman rule itself is momentum dependent. So for fixed external momenta configuration, this is Feynman diagram, but off-shell external momenta. For given momenta configuration, other permutation does not give me the same answer, right? So if I stop the momentum, obviously. So for given momentum configuration choice, different permutation without the integral is a distinct amplitude. But once I do this momentum integral, you see I'm summing over all possible momenta. Eventually, this will include all possible permutations of the momenta. So eventually, given this times with this integral, this will create another n factorial permutation, eventually canceling this out. So in the end, it will be the same. But in order not to double counting or less counting, I need to do 1 over factorial explicitly here. I know, it's combinatorics. Do you think I like it? Well, I have to take the responsibility. Okay, so that's that. Now, so for instance, if you wondered about minus sign here, y plus sign, maybe that version is the arrow out, but probably you can also define arrow in by converting things. Okay? Okay, now I'm almost ready to answer another physical meaning of this object. So we started out by saying that let's define this being a sum over entire Feynman diagram with the external legs of shell, putting the propagators there, right? That's what we did. What is that? Another independent physics meaning of that, or not independent, but like related to physics meaning of that. To do that, let me just do the Fourier transform of this. Okay. One way to do that is to unleash the job. So let's Fourier transform. So one way to do that is to brute force, meaning what? So f tilde of k, if you have dx, this is a one-dimensional version, I, k, x, rho x. So either you just, oh no, where the rho comes from? F. So for instance, you just do it, meaning you just write down all this function of momentum into that expression, do n integrals, n delta function, blah, blah. Go and enjoy. Or if you happen to remember, which is basically the same thing, this is equal to k. Okay? So either way, you can do it. So either way, it's not an independent different thing, it's basically the same thing. So then you can check that that is equal to as you'd expect, probably. Okay? Just replace K's with X. Okay, is this useful? So now we have a position space version of that figure there. Okay, suppose now you arrive at this. Can you think about a physical meaning of that function now? So in momentum space, we defined it as the sum of all these 5 diagrams, right, with offset blah blah blah. Now, if somebody hand you this, on the other hand, with understanding that rho appears as this way, can you come up with another physical meaning that this function encodes? What does it do? So to this end, let me write an equation probably you have seen in E&M class or some other class. Does somebody know the name of this at least? Green's function. Then, does somebody know the physical meaning of this?
For this form of that function, it is a response of that.
Response. So if you kick the system like this, external source, there's a system that you want to study, okay? You kick it, ask what does it do? So this is called a linear response function, or Green's function. Linear because it responds to the one linear power over external sources, right? It's a linear response. So the quantum field theory, what do you get? You get infinite number of Green's function regarding to any number of external reaction, right? Any function of action done to the system. So you can ask, hit once, what does it say? With the 2 simultaneous, what does it say? 3 simultaneously, what does it say? Million simultaneously, what does it do to you? Right? So therefore, in this case, Fourier transform of the diagrammatic definition that we had is nothing but a nonlinear in general, Green's function of this quantum mechanical system does. You can say, what exactly? What exactly is that response? That exact response is captured in this diagram. So let me draw it again, and then I will just explain to you. After that, I will ask one question. And then probably I should answer that question next time. So this was the diagram. Well, now personally, I have to spend more time to finish this diagram. So now, let me take this as my time axis. And let me draw a boundary. So, which state is this? What state is this, do you think? Okay. The vacuum. Okay, so this is the vacuum. So this is the vacuum. What about here? What is it? It is vacuum. So what it does is that you're looking at the vacuum to vacuum transition, but in the presence of a source, what you can do is that you can create a particle, meaning in this case I'm translating what response function theory experiment I'm doing. Well, I'm using the source to create a particle. Ask how the theory responds to that. And I probe what result would that get you. So this is literally a response function gain, but arbitrary n number of sources and detectors. And formally, it is captured in a vacuum to vacuum transition amplitude. So this object, or momentum space version, is actually vacuum to vacuum transition amplitude in this S-metric sense, but if you introduce source in the end. So all of a sudden, arbitrary kind of scattering processes can be encapsulated into single object. If you're thinking about perturbation theory in power series of a row, you don't have to look at now some momentum to some momentum, blah, blah, blah. But in the expansion of a row, everything is captured in vacuum to vacuum transition amplitude. Okay, this picture. So therefore, we will learn that this has a nice meaning of Green's function and response theory. Now, like I said, I was just gonna ask one question. So far, the way I played out all this thing was based on my intuition, our intuition. We built from a tree level physics, right? There's Yukawa, there's this process, that process. I just devised defining a diagram with the propagator attached and the amplitude. You can ask yourself, is this type, something like this, generally true? Right? Would something like be generally true in all in perturbation theory and for any quantum field theory? That's a tough question, and that's an important question. So next lecture, I will basically discuss that there is a version of this discussion we can do, and in fact, there is a nice equality that some version of this thing we can define next time, okay, and can always be represented as a Feynman diagonal expansion beyond the tree level and any order perturbation theory for any QF, well, perturbative QF. Okay, so that will be the topic we'll discuss. Thanks. Oh, somebody raised their hand or something?